Hello and welcome to my channel. Today we're going to look at very interesting actuators from the company MyActuator. This is affordable quasi-direct drive actuators, so they should be good for the fast robotics, like for example for the robot dog or for the robot cat, whatever you prefer, or for the fast robot arm. Okay, let's get closer look at these actuators. I have two models of actuators. This is X8 and this is X8 Pro, 4 in total. And also with these actuators I have this bag with some connectors, some wires and USB to serial port adapter. This all is very useful. Let's open our actuators. This is some tips about how to attach these actuators and what kind of screws we would need for each model of these actuators. Now let's look at actuator. Ta-da! RMD X8H. There is a planetary gearbox inside with a reduction ratio of 6. And this is actuator itself. I can feel a tiny backlash. Over here there is a connector for the CAN bus. Here the CAN bus is already soldered, these two wires. This is a power. It's from 24 volts to 48 volts. And over there is a small connector for the serial port. For this USB to serial port adapter. The actuator has the screw holes for mounting from the back and from the front, where there is output shaft. Over here it's the same. Now let's look at the Pro version. It should be a little bit larger, heavier and more powerful. X8 Pro. This is larger. It's definitely heavier. So this is a Pro model. V3. Also it has a planetary gearbox with a reduction ratio 1 to 6. But otherwise it looks the same as the other one. Here you can see the parameters of these two actuators. This is for the X8 actuator and this is for the X8 Pro. The main feature of these actuators is that they have the second encoder at the output shaft. So they have the encoder on the motor side, as most of the actuators, and they have the second encoder at the output shaft. Like this, these actuators, they can compensate the backlash, or at least try to compensate this backlash. And of course we're going to test this second encoder. Here I have prepared all the parts to test these actuators. I put the connector to the CAN bus. Here there is an Arduino Uno with the CAN bus shield, with appropriate connector for the CAN bus. And by the way, over here I put the termination resistors. USB to serial adapter, which I received with this actuator, and the 48 volts power supply. And I have also prepared some 3D printed parts to fix this actuator. Let's start with the smaller version, not the Pro one. I'm fixing this piece to the output shaft. Like this, it's easier to see when the output shaft is going to rotate. The serial port is over there, so it goes like this. Connected. Power. USB goes to the PC. This is my tiny Windows PC. And in terms of the hardware, we are ready to test. For the initial test, I'm going to control the actuators through the serial port. Like this, I don't need the CAN bus. Like this, I don't need to write the program on the Arduino. So it's going to be easy and simple. And like this we can use the dedicated software from the MyActuator company. Switch on the power for the first time. Power is on and we can see this over here. Now let's run the dedicated program for the test. But normally I think the best way to control this actuator is through the CAN bus. But with the serial port at least you can test it. This is a program, Assistant 3.0. It has several tabs here, so this is the first tab where you can run this actuator. We can also plot the shaft angle, the speed, and the current is already plotted, so if we rotate by hand, we see the speed changing, the position is changing. Cool. And also we see the shaft angle over here, the value of the shaft angle. Other tabs. There is some parameters, probably the most important one is here, CAN ID. There is also some PI parameters from the PID loop. This is some advanced parameters, some another PID loop parameters. Here the parameters for the motion, like the position, max, min position, the maximum speed, maximum acceleration, and the same for the speed mode. Here there is something about encoders, I don't know exactly what, and here you can update the firmware and you can read the firmware version. I have this one. Okay, now let's go to the running and let's try to rotate it. So you can rotate either with incremental angle. Let's put plus 100 degrees. 100. Go. And it rotated approximately 100 degrees. And this is absolute angle. Let's go to the absolute zero angle. Let's look at the current. Current seems appropriate. So when there is acceleration, deceleration, and you see the current values. Now let's rotate with the constant speed. Let's try the small speed, the slow speed. It seems like it rotates. Yes, it does. Try the higher speed, 100. Yes, it rotates. This is a quasi-direct drive actuator, so the speed which it can do is much higher than this one. This is just for the illustration. Okay, let's stop it. Let's go to the 0 degree. Cool, 0 degree. Yeah, it seems like it works. Great. Now let's check the secondary encoder. In order to test the output shaft encoder, I'm going to switch off this actuator, and when it's off, I'm going to move the actuator, the output shaft, at some position by hand, and afterwards I'm going to switch it on and see if it's like reasonable values, which is showing. So let's do this. Now let's switch off the actuator. Now the actuator is off. Let's move it approximately 180 degrees. Something like this. And let's switch it on and let's check where we are. Power on. And as you can see, it shows that the shaft angle is 175 degrees. This is cool. Perfect, it works. Ha ha ha. And the same kind of test I'm going to do with the Pro actuator, just to check that it works at the same manner. Switch on the power for the actuator. This is the first time for the Pro version. Power is on. Here the LED lights up. Now let's run the program. The program is running. Everything seems fine. Motor status, motor OK. The position is OK. And now let's try to move it. Let's try to move it to the 0 degree directly. So let's try to move it with the speed 100. Yeah, it works. Let's plot the speed here. Let's plot the shaft angle here. Let's stop it now. And let's go to the 0 degree. Okay, it was faster. So probably the maximum speed here is more than 300. Yes, here it's written 500. So it's set here at the 500, the maximum speed. That's why it was rotating faster. And this is not the maximum. The maximum is way higher. Now let's switch it off. It seems like it's off, so we can rotate 180 degrees. Approximately 180 degrees. Switch it on. And let's check the position. 184. By hand, I can rotate with a precision 4 degrees. Not bad. And so it seems like encoder at the output shaft for the Pro version also is working. Now let's test if we can control this actuator using the CAN bus. So the serial is disconnected. CAN bus is connected to the Arduino Uno with the CAN bus shield. And on this CAN bus shield there is a small joystick, so I would be able to go forward or backward with the actuator. And also I have left this actuator at exactly 270 degrees. So let's see if we will be able to read this data through the CAN bus. Fortunately, this actuator comes with a really good description of the control protocol. In our case, we're using CAN bus, but you can also use the RS485 if you have the actuator which supports RS485. I have the CAN bus because I'm more familiar with the CAN bus. And from here, we're going to use mainly two commands. So we're going to use the command 9C in order to read the position of the actuator. And we're going to use the command A4 in order to send the command to move this actuator in the new position. So this is a protocol. It's well described here actually. So this is a really nice document. And now let's look at the Arduino program. This is an Arduino program. Over here, first I read the position, the initial position of the actuator, of the output shaft. And I put this initial position in this variable, genpods. And after I can move this variable with the joystick. I can either increase it or decrease it. And I send the command to move the motor over here, and afterwards I read the position of the motor. Actually, this command is not really necessary here, because when I send this command, in the reply to this command, there is a position, information about position. So we can get it here. But for the educational purpose and for the purpose of the simplicity, for the moment I'm doing it like this. Power to the actuator. And let's check our serial monitor over here. So the power to the Arduino. The position 272. So it's almost 270 degrees. It's 272 degrees. Good enough. So this is the position, and now I can move it. So like this the position decreases, and like this position increases. It works. Aha! The only thing that it moves in the steps, as you can see. And I think the main reason for this is because this actuator made in the way that it waits for the command and afterwards it executes command. So it does not really like when you send one position and before it executed this position, before it went to this position which you sent, you already sent another position, the new position to go. And like this, it's never reached the position. I think this actuator does not really like this. What it likes is that you send him the final position where it should go and you don't send any new position, any new command in between. Yeah, I think this is how it's made. With Arduino it works. This is great. I would just check that also the Pro version of the actuator also works with Arduino, but I don't see the reason why it should not. So I'll do this quickly. Again, I left this actuator at the position 270 degrees, which we should see on the serial monitor. Power to the actuator. Let's clear the serial monitor. Power to the Arduino. Now it works. It reads 268 degrees, which is quite close to the 270. So this part works. Now let's try to move it. Yes, it does. Yes, it does move. So we can control it with Arduino with the CAN bus. So it works. As the next step, I would like to measure the backlash. The backlash is basically the play of the output shaft due to the imperfection of the gears. And almost all the planetary gearboxes, they do have the backlash because it's quite expensive to make zero backlash gears, because they should be like super precise. And needless to say that the backlash is super important because it's going to influence on the precision of the robot, and also it can influence on the vibrations in the robot. So it's always better to have the lower backlash possible. So I'm going to measure the backlash over here. It's a good idea to measure the backlash not in one single point of the shaft angle, but in different points of the shaft angle. So what I'm going to do, instead of moving the shaft angle and measure different angles, I'm going to move the actuator with respect to this holder. And I'm going to do this over here because there is a lot of mounting holes. So basically I'm going to move this actuator with respect to this mounting hole, so I will have some discrete values of the shaft angle. Yeah, something like this. So basically I'm going to do several measurements of the backlash at different shaft angles. And here's the results of my estimation. This is for the X8 and this is for the X8 Pro. I did the 5 measurements with each actuator at 5 different output shaft angles. And for the X8 this corresponds to the backlash plus minus 70 arc minutes. And for the X8 Pro this corresponds to the backlash plus minus 5 arc minutes. I don't know why there is a difference between these two. I would expect to have the same, but probably they use better gears for the Pro version. Now let's continue with the torque measurements. As a next step, I would like to estimate the torque, just to see that this torque is comparable with the torque from the specification, and for this I'm going to use this beautiful torque machine. It has the controller over here. This is electromagnetic brake. So this is the shaft of this brake. You can see it over here. And this device is going to measure the torque. So the actuator is going to be placed between this part and this shaft. The actuator is going to rotate this shaft. The brake is going to brake this shaft. And this device is going to measure the torque which produced by the actuator. I'm going to start with the less powerful actuator. So we have the shaft angle, the speed and the current. Now let's go to the direction -100 and start. I'm going to increase the braking power. 6 Newton meter, 7 Newton meter, 9, 10, 18, 12, 15, 18. And the temperature is 52, 53, 56, 57, 60. Decrease. Stop. The temperature is 70 degrees. So it can handle triple of the nominal torque, but for the quite short time. And what if I do the nominal torque? 6. This is the nominal torque. The temperature is 42 degrees. And as you can see, at the nominal torque, the temperature rises quite slowly. It goes up nevertheless, but quite slowly. And now the torque measurements of the Pro actuator. Now I'm going to run it with 100 RPM, constant speed mode. 8 Newton meters was the nominal torque, now it's 9 Newton meters. So this is double torque, double nominal torque. And this is almost triple torque. Stopped. Something happened. I don't know what happened. We went to the 23 Newton meters, almost triple torque, and approximately to the 20 amps. So probably we was too high at the amperage. The stall current 20 amps. So we reached the stall current. Okay, it was almost triple torque. Good. Let's try to run at the nominal torque. So I'm increasing the braking power. 8 Newton meters, 8.1. The temperature is rising really slowly. Yeah, the temperature is rising, but quite slowly. Let's see how long we can run this motor at the torque close to the triple of the nominal torque. So let's start rotating. Let's slowly increase the braking power. $22. Cool. We leave it here for the moment. The temperature is rising. 54, 56, 57, 60, 61, 63, and here I will 67. Here I will go back. So as you can see, it can sustain the almost triple nominal torque for quite short time. So with a nominal torque load, both actuators can run for quite significant period of time. And even both actuators can triple their torque, but for the short amount of time, maybe 5 to 15 seconds, something like this. The X8 actuator can really triple their torque, and X8 Pro can almost triple their torque. With the triple torque, the temperature of the motor rises quite high. And fortunately, both actuators, of course, they do have the sensor at the motor windings. Like this, you can check this temperature, and if it's too high or if it's too low, you can understand if you should wait till the motors cool down or you can push it a little bit more. Another important advantage of these actuators is the secondary encoder at the output shaft. This is a really cool feature. Another great advantage of these actuators is that they perform really well at the low speed. The motion at the low speed is really smooth. And I've tested many quasi-direct drive actuators, and most of them, they are not performing really well at the low speed. But these two, they work really good even at the low speed. Also, these actuators, they can bear the radial load, as most of the actuators, but also axial load and quite high axial load. I think this is a great advantage. And I should say that both actuators with respect to other companies are quite affordable actuators. Maybe the only disadvantage is that these actuators, they don't really like when you send a new command before the previous command is executed. And this is, I think, what happened when we tried to control it with the joystick. In this case, we had this motion with the steps. And probably in order to avoid this, when we controlling with the joystick, we should not use the position control, but probably we should use the speed control. In this case, probably it's going to be better, but this needs to be checked. So be aware about this. But overall, I really like these actuators. They're quite nice, solid, affordable, perfect. And I'm going to use them in my future videos. Thank you for watching this video till the end. Huge thank you to people who support me via Patreon and via YouTube channel membership. Here are their names. Thank you guys and girls, you are the best. As usual, stay safe, good luck with your projects, and see you next time.